Welcome to AskeyGeek.
Hey, if we haven't met already, I'm the digital avatar of AskeyGeek,
where we build your next advantage with tomorrow's technology. And today, one of our experts is stepping in to show our latest breakthrough. Enjoy and happy learning.
All right. Look inside any major logistics center, and you will find a massive operation running on a flawed premise. It only reacts after a problem occurs. Waiting for inventory to drop before taking action inevitably creates two fatal conditions. You either run out of stock entirely, bringing sales to a halt, or you panic buy, trapping vital operating capital in excess product sitting on shelves. The tools used to manage this are usually static spreadsheets. A grid of rows and columns has no capacity to observe a sudden spike in demand or a supplier delay on its own. It waits for a human to hit refresh and interpret the numbers. We can now replace that manual dependency with an autonomous system. By wrapping a large language model in a specific architecture, the AI moves past its role as a passive chat interface and starts actively managing the data. We deploy an LLM here as a persistent 24/7 operational manager. It identifies inventory gaps and builds the necessary reorder documents before a human even identifies the problem. To build this deterministic system, we organize the AI's environment into three specific layers. We call this the DBS framework. The top tier is the direction layer. This acts as the logic engine, or the manager. It is a strict markdown file that dictates the exact sequence of operations the AI is permitted to run. Below that is the blueprints layer. This is the system's persistent memory. It stores your specific operational constraints, proprietary vendor lists, and safety rules, ensuring the AI applies your exact business logic to its decisions. The final tier is solutions. These are the programmatic hands of the system, Python scripts and API connectors that allow the AI to push data, run calculations, and trigger actions outside of its native text capabilities. This structure eliminates the unpredictable nature of a standard chatbot. Instead of a highly variable chat interface, you have a rigid, repeatable pipeline. By interlocking direction, blueprints, and solutions, we convert an otherwise open-ended language model into a highly focused inventory manager operating system. To see how this operates in practice, we start by engineering the very beginning of the logic pipeline for our inventory system. An autonomous agent needs a mechanism to wake up and initiate its workflow without a human typing a command. We establish this through a data pulse. We configure a scheduled task to fire on a strict 24-hour cycle. Every day, this pulse commands the agent to scan our primary stock file, the inventory.csv. An analyst might run this query once a week, or whenever they suspect an issue. The automated pulse guarantees daily evaluation. Upon activation, the agent immediately extracts the active SKUs and their volume levels from the raw CSV data. This daily extraction isolates exactly what is currently sitting on the warehouse floor, forming the absolute factual baseline for all subsequent decisions. By setting up this pulse, we remove the initial human bottleneck. The system is now continuously observing its environment. Once the raw data is loaded, the direction workflow instructs the agent to analyze the trajectory of those numbers. This chart shows an item's volume dropping over time. The agent calculates sales velocity, how many units leave each day. Using this, it projects the trend forward, calculating the exact date this item hits a zero balance. An unconstrained system would wait until that date approaches to act. Here is where we inject the blueprints layer, applying our business-specific constraints. We establish a hard rule. All top-selling items must maintain a 15% safety buffer. The agent reads this rule and recalculates. The critical threshold is no longer absolute zero. It is the moment the stock hits that 15% line. By shifting the target, the agent ensures we never reach the point of paying premium freight rates to rush an emergency shipment. Integrating blueprint rules directly into the sales velocity calculation turns a basic forecast into an automated risk management protocol. Knowing when to order is only half the equation. To execute an optimized procurement strategy, the agent needs to know who to order from and at what price. The moment a SKU is projected to breach the 15% threshold, the workflow triggers a new protocol: gather external market intelligence. The agent launches a live web search for current supplier data, actively scanning for sudden price drops, bulk discounts, or shifts in shipping lead times. We restrict this autonomy through a second blueprint constraint, ensuring the AI only interacts with verified sources. The agent cross-references every live search result against a static vendor list.xlsx file. It filters out all the noise and restricts its selection strictly to suppliers that hold a gold rating in our system. This filtration step guarantees that the agent's autonomous sourcing is tightly bound to pre-approved business relationships, completely eliminating the risk of rogue purchasing. With the math calculated and the vendor verified, the pipeline reaches its execution phase. The primary trigger condition is met. The system identifies that a high-velocity SKU will cross the 15% safety buffer in exactly 7 days. The immediate response is to spawn a flashing red low stock indicator on the internal dashboard, alerting the team to the impending shortfall. The system moves immediately from identification into the execution phase. This is where the agent triggers the solutions layer. We activate a specific CSV connector or Python script that handles the external output. This connector ingests the agent's calculated reorder quantities and the vetted gold tier vendor selection. It automatically formats that raw data into a pristine purchase order artifact. The line items, optimal quantities, and vendor terms are all perfectly structured. The solutions layer crosses the boundary between digital analysis and physical operations, delivering a finalized procurement document that just requires a human signature. If we step back from the mechanics of an individual purchase order, we can evaluate the aggregate economic impact on the business. Implementing this pipeline shifts the role of an operations engineer. Instead of manually hunting for stock discrepancies, they spend their time optimizing the overarching strategy. This dashboard shows the macro-level output of the Inventory Manager OS. Here, we track projected revenue against total inventory cost. The dashboard tracks the efficacy of the safety buffer logic, illustrating how many potential stockouts were identified and intercepted before they disrupted the sales floor. Concurrently, it tracks the reduction in excess warehouse stock, proving that operating capital is no longer tied up in unnecessary overordering. Language models have outgrown their origins as simple text generators. When properly engineered, they operate as reliable, deterministic systems managers. The strict isolation of logic, memory, and tooling, the direction, blueprints, and solutions layers, is the exact mechanism that forces an AI to execute with absolute consistency. Mastering this three-tier architecture allows you to convert reactive logistics into a system that maintains its own operational equilibrium.
All right, that's the update from the lab for today. I hope you learned something new. Head over to AskeyGeek.com